So good morning. Welcome to the next edition of our series of LCA trainings of the Planet's SSbD training program. Today we are diving more deeply into environmental life cycle assessment. And I shall say thanks to the presenters and the designers of this training, Thomas Hennecker from TNO, Carla Caldera from Ciensco, Luelia Fuhet from IPC, Laura Maniasco from RINA, Ponema Nagesh, Radboud University, and Stephanie Desrousseau from CA. Also Eva Hahn from WACA was involved, and of course, many thanks to Beatrice from BNN for helping with the mural and the Menti and organizing everything so smoothly. Thanks for your very engaging and motivated way of designing this training series, which is really working out, in my view, very, very nicely. What are we going to do today? So I will give a very, very short intro and a little bit of recap from our initial training, from the introductory training on LCA from last time. And then Thomas is going to take it to the goal, scope, and inventory. Also, Luelia and Laura are going to be presenting content, and we are going to have a very intense and interactive, nice session where we are breaking out into 5 different breakout groups, and our moderators there will be Carla Caldera, will be Thomas Hennecker, will be Luelia Fuhet again, and Laura Maniasco, and also Stephanie Desrousseau and Ponema Nagesh in the breakout rooms. Where we are going to be working on the mural, where we practice a couple of steps that we need in this LCA. Good, and then we are also going to be talking about sensitivity, about uncertainty, about prospective analysis. Let's see. And we are going to be wrapping this up then. We expect this training to be taking about 2 hours. In total, we were aiming at a bit less, but in the end, content was so nicely accumulating. So I guess we will be finished by 12 CET. Well, yeah, we know that we are a project working on SSbD, and there we have this endeavor to combine safety with sustainability aspects and design novel products, innovative, advanced materials, chemicals for the future. So we have this endeavor of these different dimensions, and we see here in red the safety, the sustainability in green, and the design functionality aspects of the different materials. We, in our project, work according to this plan that we have after our scoping analysis and SSbD plan, and do the assessment at different tier levels. And LCA is one very important element of the sustainability assessment at the different levels. At the tier 1 level, we need a more prospective view. So therefore, we also look a little bit into, for example, prospective LCA today towards the end of this session. There are also some elements of safety-related end or midpoints in LCA. We will touch upon that slightly. You will see that. So LCA is covering also a little bit of safety. So we are integrating also a little bit different dimensions of SSbD. As usual, this session will be recorded and will be shared not just within our project, but beyond that with the entire community being interested in safety and sustainability of chemicals and materials. And this adds to an entire series of different topics that we have already partially tackled, and others that will still come. For example, a more deeply designed series on safety-related issues. So we did already scoping, we did tier 1 assessment, some QSAR training already, but more will probably still come. Fair data and digital product passport training. And our introduction to LCA is also already available, as usual, on Zenodo, also on our homepage for our project. But the materials are deposited at Zenodo, so they are permanently available there beyond project lifetimes. Also, we have a YouTube channel where materials are, the recordings went, and also the mural which we use is deposited in this Zenodo collection and can be used for interactive trainings afterwards. What did we do in this introductory training? So we were diving into this life cycle thinking. We did introduce many things, many aspects already of the different types of LCA. So we were also looking a little bit into overviewing life cycle costing, for example. We were also very, very quickly touching upon what social LCA is, but we were also then looking deeply into or overviewing at least the different phases of LCA, so the goal and scoping, the inventory phase, the impact assessment, and interpretation. So these phases we are going to be diving more deeply into today. We are also going to be talking about MCDA and uncertainty in another session later on, and we will touch upon uncertainty once again today with sensitivity analysis, for example. We did already talk a bit about that, but we had a bigger focus in this very first training on, for example, practicing what is a functional unit, how we define functional units. So we had an interactive session on that one in these breakouts at that first training. And we also looked what is a reference flow. So basically this amount needed to fulfill the functional unit which you define. So this was also practiced last time. Also system boundaries, we touched upon that. So this was actually done last time. There was this very nice example with this pen versus the ballpoint, where a functional unit was defined. Very interesting to look into that, and we base our training of today on that content from last time. And with this, I would like to give the floor to Thomas to start basically with the training on environmental life cycle assessment more deeply today. And I guess you will be sharing yourself, right?
Yes, I should be sharing already. Yes? All right. Thanks for the intro, Martin. Thanks everyone for joining. It's nice to see you all here today. We're zooming in from SSbD to sustainability, from sustainability to environmental sustainability, and environmental life cycle assessment in particular. I'll start us with some refreshers from last time. Martin did a little bit of it already, but I'll go a little bit more detail into what we looked into last time when we were looking generally into sustainability. Starting with the main 4 phases of life cycle assessment. Life cycle assessment, particularly environmental life cycle assessment today, is a modeling tool or a family of methods that we use to assess sustainability. Yeah? All right. Okay. That we use to assess the sustainability of products, of chemicals, of materials, of services. And it's regulated by a number of standards into those 4 steps: goal and scope, inventory, impact assessment, and interpretation. Those 4 steps, you can see it on the right here, are interconnected to one another. The idea with this interconnection is that the process is iterative with short loops and long loops. So you might define your goal and scope and start building your inventory and realize it's a mismatch between your inventory and goal and scope and already immediately go back to your goal and scope. Or you might go all the way to your interpretation and realize there was something wrong in your inventory and try to redefine it. It's a very important aspect of LCA, I think, this iterative nature. And we're going to go now more into detail into each step with the goal and scope where you set the scene, the inventory where you build your model, your inventories of inputs and outputs, your impact assessment where you convert them to recognizable units like kilograms of CO2 equivalent for climate change, and interpretation where you try to figure out conclusions from all these results. Let's start then with goal and scope. So I said it, goal and scope is about sort of setting the scene, having a basis as strong as possible to have robust next steps, let's say. There are 5 sub-steps into this first step, and we'll look at the first 3. We have to define a goal. That's not surprising, I think, in the goal and scope. We have to define a scope in the shape of a process flow and system boundaries, and we have to define a functional unit. This is basically what we did last time, so I'll remind us what we did together. The goal that we're going to follow throughout this whole first 2 steps is going to be a comparative assessment of 2 paints. So it's I don't know, maybe a construction company that wants to do a large amount of painting and then has choices between paint A and paint B, and they come to you and they want to figure out which one would be most sustainable. So they ask you to compare the life cycle environmental impacts of this paint A, which is water-based and requires a certain amount of coating and has a certain number of characteristics, versus paint B, which is solvent-based and has different characteristics. The first thing you'd want to do is sort of think about the life cycle of your paint. What does it look like? This is where you try to draw system boundaries. This is the whole idea of life cycle thinking, that even though you have this company that is focused on the use phase, you want to think about everything that came before and everything that came after, upstream and downstream from the use phase in this case. So you go all the way from raw material extractions for paint to manufacturing, transportation, the actual use, which is maybe what we're focusing on with our goal, and the end of life of this paint with potential for some circularity here. And you can decide for yourself what type of system boundaries you want to draw around this, what part of this life cycle you should include in your analysis. Maybe from the cradle to a gate, one of these processes you could stop there, or from a cradle to the grave, or maybe cradle to cradle even if you have circularity. And this scoping, these system boundaries should be aligned with your goal. Typically, unless you have any reason to do otherwise, you should focus on cradle to grave. In a comparative assessment, if you're really certain that the use phase will be the same for two products, you could then stop at a gate. That would be an example. You might find in the raw material some pigments, some binders and resins, solvents, surfactants, and others. In the manufacturing, you would want to take those raw materials and mix, disperse, blend, have your paint, and then package it and distribute it. In the use where you actually apply the paint to a wall, you will need some brushes, some buckets, maybe some gloves. You might need some maintenance. If you want to have paint in the building for 40 years, but your paint only lasts 10 years, you might need to reapply every 10 years, so maintain this paint. And at the end of the life of the paint, you might want to remove it, might require some extra products like paint stripper. You may have some leftover paints, like let's say use phase waste, and you might need to dispose of this waste. In our example, we're going to take a cradle to grave approach, so including all of this, because we expect that between paint A and paint B, there might be differences at every stage. So we need to account for all of these stages to avoid missing out on any trade-offs between those two paints. So that sort of sets the goal and the system boundaries. Now we can work with a functional unit. Last time in our previous training, we had a hands-on exercise on this functional unit where we worked together to define a functional unit, but I'll pretend that we didn't and re-ask this question so to define a functional unit is something that allows you to fairly quantify the function of the product, service, material that you're looking at. So it's sort of the denominator in all of your analysis. You're going to express impacts and inventories per this functional unit. And it should be made in a way, it should be defined in a way that lets you be fair in the comparison of the two paints. So here I have a few examples of what a shortened version of functional unit might look like. You have 1 kilogram of paint, 1 bucket of paint, manufacturing one of those two. You have painting for a certain amount of time or painting for a certain amount of surface. And yeah, I'm going to go a little bit fast in the interest of time, but let's say the first one, for example. If I do 1 kilogram of paint, maybe you can already see it would not be fair to the two paints, because you can see that one of them requires a single coat, the other one a double coat, that they don't have the same covering power. So with a certain amount of paint, I can cover more or less of the wall. So if I focus on mass, then I would be unfair to the paint that can cover more wall with less mass. I can make similar arguments about a bucket or about a number of time. However, if I focus on a certain surface area, then I should be able to focus to capture fairly the functionality of two of these paints. And what we did last time is go into more detail and more rigor on how to define this. So we have these two paints and we together define some obligatory properties. So what does the paint really need to do? What is the true function of this paint? And some positioning property. I'm going fast because we did this already, but I hope you can follow. This obligatory property would be the paint should paint, right? It should cover the wall. You can start there. We were considering an outdoor paint, so we should protect the wall against weather. It should meet certain health requirements during application. It should last a certain amount of time, etc. Positioning properties are things that are not fundamental to the function of the paint, but are still nice to know, and these you would document rather than quantify them in the functional unit. So the speed of application, the drip-free for consumers, maybe what variety of color tones for certain brands. And then if you take the properties to the left, those that are obligatory, and you put them into a functional unit, you end up with something like this. That's the complete version of the functional unit. So you want to coat and cover a certain surface of an outdoor wall, following some predefined health standards that would survive under certain predefined weather conditions with a given color and for a certain amount of, what do we call this, lifetime, 10 years in this case. If we use this functional unit for paint A and for paint B, and we relate functional unit to the characteristics like number of coats, covering efficiency, let's say, and the lifetime that the paint lasts, we can define a reference flow. A reference flow is the amount of paint A and the amount of paint B that is needed to meet this functional unit, to fulfill this functional unit. Again, we did this last time, and if you, like I said, combine the coat, the lifetime, and the covering power, you end up with a little bit more of paint B needed to fulfill the same function than paint A. So 3 liters for paint B and 2 liters for paint A. And hopefully this shows you how this functional unit allows you to fairly compare the two paints and any other paint for that matter. So you can also harmonize for studies outside of your own. It does that better than the kilogram or the hours of painting. Now, that's the way that we set the scene. And once we've done this, so we've defined our goal, we define our scope, we define our functional unit, we want to build an inventory. So we want to, like it says in the text on the right, list everything that comes in and comes out of your life cycle, of your processes. It might look something like this. Again, this should be a refresher, so I'm not going to spend as much time as I normally would, but I hope you can follow. You want to model all of the inputs, so energy and materials going into your system, as well as, let's say, raw materials going into your system, like water and minerals, and also everything coming out of your process. Products and wastes, so in the case of paint, the actual paint should come out, but also everything that is wasted during production or use, and as well as direct emissions during your life cycle stages. Emissions to different compartments, air, water, and so on. These can be divided, these are all exchanges between your process and the outside of your process. And you can categorize them between the technosphere and the biosphere. The technosphere being sort of other processes that are human-made. So for example, electricity production, if we're going to talk about energy. And the biosphere is nature, everything non-human. So really water from a lake or emissions to the air, to the atmosphere. You will do this as inputs and outputs, and then for all of the 4 general life cycle stages that we've been looking at. I think it's easier to grasp this if we look at an example. So let us take this table and sort of apply it to one of the raw materials in our life cycle of the paint production, of paint. For surfactants that are used into paint, it might look something like this. So again, input and outputs and a number of items. You can classify them using the same sort of color coding of technosphere in purple and biosphere in green. And you find technosphere inputs like energy at the bottom here that we've been talking about, electricity and heat. You find also biosphere input like water from a lake or crude oil from the ground that it uses feedstock. And then you find the same thing in the output. The actual surfactant is your technosphere output. You have some waste that needs to be treated. It goes to the technosphere as well, production waste or wastewater. And you have maybe some direct emissions during the production of that surfactants, like particulate matter, dust, or organic compounds that are volatile. Right, this was a little bit fast, but I think I've walked you through a refresher of what we did last time. The goal and scope, set the scene, and the lifecycle inventory, an example of how this is built. We're about to go into a hands-on exercise where you will try to do this yourself. But before we do this, before we drop you in deep waters, do you have any questions about this high-speed refresher? I see some head shakings, so maybe not. Right, that's okay. You'll have plenty.
Everybody is very keen on doing this in practice and discussing it in the breakouts in more privacy, and then many questions will come up.
You will have more chances to ask questions during the breakout, indeed. So let us go there. Yeah, I just realized the title of this slide is a little bit misleading, but never mind that. We're doing inventory building. It's your turn to go. You will define or build an inventory together using a mural and in breakout sessions. You can scan to join the mural, or I believe it's already as a link in the chat. Excellent, thank you, Beatrice. You will have the same goal of the two paints, and you will try to go and look into paint A and build a very simplified inventory for the life cycle of paint A, based on some information that is provided to you by different stakeholders over the life cycle that we've collected for you conveniently. So you'll try to look at the table and inventory and try to define these input and outputs together with a moderator. You'll have a few questions to guide you through this, and a moderator, him or herself, to guide you through that as well. This will be about half an hour. You will be called back to the plenary anyway, and we'll have a chance to discuss what we learned and the main discussions that we had in separate groups. Anything else to add, or shall we just jump in? All right.
So hello back. I hope I have not interrupted you too much.
No, it was the right timing.
Anyway, we have saved a bit of time. Shall we make a short reporting back from the rooms?
I think so. It would be very nice to hear what challenges and questions and discussions you all had. Maybe we could do this with an open floor, or shall we hear from the moderators? Not sure. Didn't think of this in advance. The open floor. If anybody wants to say anything, moderators or otherwise, exciting stuff you discovered, exciting questions that you answered or didn't answer, we would like to hear from any and all of you.
As a moderator, one interesting thing that we had in my room was how do we consider the milling machine, for example? And we don't have any info for this example, but it was interesting to have those questions.
So what's the answer?
The answer would be, it will be a very small amount because it will be divided by the number of years of use and of course the number of liters per year. But we didn't have the info, so I couldn't give an estimation.
Yeah.
But yeah.
Yeah, all of these, you can think of them as capital goods emission, almost like CapEx emissions, equipment, but also infrastructure, the building itself for the chemical factory, for example. Or when you think about transportation, the truck itself, the production of the truck, they're all divided by a long lifetime where you can make and transport a lot of liters of paint. So then the impact per function unit becomes very small indeed. Mario, you had your hand raised, but maybe it was the same point.
Yes, So a question that just came up is how do you weigh if a source from the biosphere, for example, water, is better than from the technosphere, like a solvent or wherever it was human-made? How do you say, okay, you harm the environment because you need a lot of water as a solvent, but the chemical would be better in this direction, but it has like harmful impact on the environment, for example. How do you decide? Is it then based on the location? Because, for example, in Austria, we have a lot of water, and in different countries, they need it for the farms or whatever. So how do you decide at the end? Because I think the location is an important point.
Yeah, that's a really exciting question. There's two parts of an answer, I think. The first part is databases, and I'll come back to this afterwards. A lot of these different flows, we have life cycle assessment of, that we don't need to do ourselves, but we rather rely on secondary data sources like databases. And I'll show you a little bit about this later, so I'll come back to that point. But the idea of location, that's really interesting. Because yes, using water in the Netherlands or in Austria is not going to be it is not going to have the same impact than using it in Spain, south of Spain, for example. The amount of water in meter cube is the same, but the impact on the scarcity of water is different. And we have, I wonder how much I can say about this without getting into too much detail, but there are different ways to look into those impacts. Some methods will look purely at the amount of water, meter cube, liters. Some will look at the effect on scarcity, so a little bit further down, let's say, the cause and effect chain. And some methods are very general, with big blocks of Europe, US, whatever. Some methods are really precise. Countries or even grid-based kilometer square type of methods. And it's all going to depend. It's all going to depend on your goal and scope, what really you're trying to look at, how much detail you need to look into this, and on your interpretation phase as well. If you find that those water flows are particularly impactful, then you need to look back. Maybe you even need to change your method. You really need to focus and get as much detail as you can. It's a really cool question. Thanks a lot. I hope I answered at least partially. Yeah, cool. Laura?
Yes, I have something to add about the meal, because before you were saying that the impacts of the meal will be very low because it will then be also divided by the lifetime, etc. And I think this is referred to the model when considering already the functional unit. But then we had one consideration already in the life cycle inventory only. The inventory is referred to 1 liter of paint. And for the first energy flow, there was explicitly stated that the energy was referred to 1 liter, but for the mill, it wasn't there. So in my group, we also noticed that if you have the time for the milling and the nominal power, first of all, you have to do a calculation. But if that nominal power and time is referred to a mill that processes a higher amount of paint, then you would also have to know how much paint is processed by the equipment and also consider this. Now, in this case, of course, that amount was referred to 1 liter because it's simplified, but it is something to be considered. And I also
maybe a quick reaction before you move on.
Yeah.
We had exactly the same discussion. I really like that, and we had a cool suggestion from my group as well to really document this. So you make, because the processing efficiency of the milling equipment is not specified, we've made the assumption that this 30-minute processed 1 liter, but that's an assumption. And that's probably something you would want to check with whoever collected the data or whoever provided the data. So this sort of documentation of the assumptions you make and calculations you make is also key to identify these little gaps like the one you just outlined. Yes, but please continue.
Then one other thing that I think is useful for everyone was the question whether the inventory has already to be referred to the reference flow of the functional unit. And I think the answer is not necessarily, because the data provider might have data for other amounts. You could even do an inventory for 500 liters of paint, as long as all the flows are referred to the same amount in the inventory, and as long as we know how much paint we have to consider in the reference flow in the functional unit. And as long as you know these two things, you can then convert the amounts to the needed reference flow.
Yeah, fully agree. As long as everything is linear. Everything in LCA is linear, so it would have to stay so. But that's typically the case. Cool. Any other exciting ideas, questions to share? Or not exciting, I don't care. Any ideas in the comments to share?
Maybe a question from my side. How similar are the results in the table in the mural out there?
Ooh. I haven't looked.
Did we somehow result in similar things, or?
I know my group has been pretty close to the solution. Is it the same for the other moderators? Maybe you can do it this way.
I think the main difference would be relevant to what you just said, Laura, because my group, we just started using the reference flow directly. So 2 liters of paint.
Yeah. And so they all look pretty similar. And also quickly a slide of a solution, so we all on the same page afterwards. But I have one more point, something very interesting. I think we discussed in my group. We had a discussion around what will happen to your inventory, what will happen to your model, if you went from paint A to paint B. So if you went from the water-based paint to the solvent-based paint. I don't know if you guys had time to have a similar discussion, but we found that, well, first of all, you would have a new input in your inventory, solvent. You would have probably no water anymore, or a lot less water. This is sort of the obvious one. But we went deeper than this. There are more consequences that will happen in your process. If you are mixing raw materials in a solvent-based paint, then surely I'm not super knowledgeable, but so I hope I'm saying this right. But the viscosity of your of what you have to mix would be different, and that might mean that it takes longer to mix it, and there are more energy in total per liter of paint, or that it's just more energy consuming overall to mix something heavier. So you might have a change there in the energy consumption of your mixing step. We also discussed different health standards around water-based and solvent-based paint. Maybe the protection equipment for workers, or the advice for consumers to wear gloves or respirators or masks would be different. And this would have to be captured in the inventory. Of course, this inventory was simplified, so some of this wasn't there. But these are things that I hope illustrate when you make a change in your inventory, there are ripple effects, there are consequences all over the place in what you need to model and what you need to think of. And in terms of SSbD, if I link back to this means all of these design choices you're making of one flame retardant against another, one surfactant against another, will have similar consequences across the whole inventory, or maybe more understandable all across your life cycle. And that's what LCA is made for, to understand these trade-offs, to understand these consequences. So I think that was a cool discussion we had as well. I think we need to move on for time, unless there is anything else.
Yeah.
You'll have more chances. Oh, sorry, Martin.
No. Good idea. Yes.
Yeah.
I guess perfect
right.
moment.
We'll move on. All right. Let me see if I can find this. So that's where we start. We had this nice mural together. This is an idea of the solution. Or not an idea, this is the solution that we propose. I think you should recognize what you have done in your own table with categorization of the inputs, the name of the input, the quantity, the unit, some comments I mentioned earlier. So as much transparency as possible into the calculations and assumptions you have made, the data sources, the temporal and geographical representativeness. Yeah, and then you connect to your functional unit and to your reference flows to fulfill that functional unit, and you think about the changes that would happen from going to paint A to paint B. Now, we're not quite done with lifecycle inventory. There is more complexity to it. We've shown you sort of a simple version of it, but there are 3 ideas: databases, multifunctionality, and industrial scale forecasts that I would like to talk to you about briefly. The first one, maybe the most important, is the idea of databases. So for now, we've been focusing on what we typically call the foreground, the system that you're directly responsible for. In this case, the life cycle of your paint and the really paint manufacturing processes. However, to enable this foreground, you need an entire background. For example, if you need electricity, you need an electricity grid, you need electricity production factories. In that electricity grid, you need steel or electric pole. To have a steel, you need a steel factory. To have a steel factory, you need some plastic packaging in there somehow. To have that packaging, you need a plastic industry. To have the plastic industry, you need the oil industry. It's never ending, this background. And it's sort of a inception fractal thing that never stops. So we have databases. Thankfully, every time we do an LCA, we don't have to remake all of the LCAs that are necessary for your background. In all of those databases, you see a few examples here, like EcoInvent, which is one of the most popular, or the European Commission database, the environmental footprint datasets. They will let you access inventory data for all of these processes. So if I were to open EcoInvent right now, I could look up electricity production for low voltage, representative of the Dutch electricity mix in 2020X. And this would give me a collection of the electricity grid, a few of the main sources of electricity production in the Netherlands, natural gas, solar, wind, and everything else that comes into the production of this electricity. And so I don't have to think anymore about the life cycle assessment of electricity. I just can stop at the level of the table we built. I have the multi kilowatt hours. I link this activity to my database. Bada bing, bada boom, I have a result with the whole upstream of these databases. There is this initiative called the Global LCA Database Access that collects a lot of these different sources of data in the same place. And you can see that there is quite some complexity already. You have different data providers, some of the databases that I was showing in my previous slide. You have different inventory modeling approaches. We didn't get into this, but there's different ways to think about the way you model your inventory, attributional, consequential, and others. Different formats for the data itself, different ways to name this data, different ways to review it. So there is, unfortunately, but also necessarily, quite some complexity to navigate when you use those databases. And actually, as LCA expert, it's a big part of our job, is just to figure out how to link this in a way that's transparent, that's consistent. Because this choice matters. Here we're looking at the results of LCA for a simple benzene production. And you have 3 different popular databases. And you can see the results across a number of environmental impact categories. We'll come back to what those are in a minute. But let us just look at a typical one like climate change. The delta in climate change between those 3 databases is like 50%. It's a big difference. So you would want to make those choices transparently, consistently, like I've been saying, and you would typically want to use one single database to be consistent across your whole background, and one single way of modeling your inventory. Now, what I was saying earlier with attributional and consequential is a fundamental choice you need to make when you deal with inventory building, in particular, when you deal with multifunctionality. The idea of multifunctionality is that in this process model that I've been presenting so far, you have inputs and you have outputs and you have a single product. But that's only one of the types of processes that we see out there. That's a single function process. There are also processes out there that are multi-function processes. So you have also inputs and outputs to the technosphere, to the biosphere, from the technosphere to the biosphere, whatever, from all of these places. But you might have two products. You can think, for example, of wood production of sawmills. You get a log, wood log coming into your sawmill, and you have a main product, that's the lumber, the actual planks and whatnot that you get out of there. But you also get the dust, the sawdust, and wood chips, and maybe even bark. And all of these things are co-products, I think, or byproducts, I think you would call them. But they can be sold for other things, like making particle board, or using, burning them to make energy, bioenergy. And in that case, you would have one process and several products. The question is, how do I allocate my inputs and my emissions and my waste to these individual products? And I have multiple choices of how I can do this. Partitioning, allocating, and expanding. And when I was talking about these different inventory modeling choices, this is one of them. I'll show you quickly what those are, so you have an idea of how we can deal with this. So you have your multifunction process, and you've chosen to do partition. That's probably the first thing you should do if you can, because the idea of partition is just to desegregate your process further with data collection. So maybe this process that you identified as a multifunctional process, if you zoom in the reality of your production, can actually be divided into product A and product B. So this has more to do with your modeling approach than it has to do with the actual reality. You just need to improve your data collection. I hope that makes sense. However, if you can't do that, if the reality is that there is really multiple products for the same inputs, what to do then? You can do something called system expansion. That's thinking about the consequences of your products. So you might have your original multifunctional process with multiple inputs, outputs, and two products. You might find on the market an alternative process, one that has its own inputs and outputs, but only yields one of the two products of your original process. And you can subtract the environmental impacts of this first AB process and this alternative process B, and you land with a virtual process that is only producing product A. This should say A, because we have B, A and B here, we subtract B, so we have A here. That's the typo. But let me give you an example. I think with an example it gets a lot clearer. With the idea of dairy cattle. So you have cows, for example, and you give them feed, you give fertilizer to build that field, and out of this you get both milk and meat. This is something that cannot be partitioned. You cannot divide that feed in a way that makes sense between the milk and the meat. But you can think of a different type of cattle, one that is raised only for its meat, and it has its own feed and its own emissions, and blah, 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 blah. And if you subtract the two, then you get a virtual dairy cattle that gives you only milk. And you can sort of virtually divide up impacts this way. But there are cases where this alternative process cannot be found. In that case, you would want to do something called allocation, and then you artificially divide these inputs, emissions, and waste based on the characteristic of your product. So it's more of a, it's a little bit of a more of a coarse approach, a butter knife to cut right through these impacts. You can think of using mass, the mass of the products that are coming out, maybe the price of the products that are coming out, or maybe the energy content of those products, lower heating value. And that would give you different divisions of all of these inputs, emissions, and wastes. And you will break mass balance when you do this, but it can still help with the allocation of your impacts. So it's more about responsibility, what we're talking about here. Yeah. I'm going a little bit faster than I'd like, but it's in the interest of time. We'll have opportunities for questions a little bit later. The last idea is what we call prospective lifecycle assessment. In the example that we worked on together, we were examining data from a mature industrial production. So it was something like 120,000 liters of paint produced a year. This is something that's been going on for a while. This is industrial level. What if this data that you collected was at the lab scale or the pilot scale, something that is not mature yet? That's something that typically happens in innovation, so in SSbD. You've collected data when you're making a new chemical, but it's with glassware in the lab rather than, batch reactors and the industrial scale. The question then is, if I model this lab scale production and I want to compare it, I want to know if I'm doing well. So I want to compare it against maybe a market reference. Then I have lab scale on one side and a market reference on the other. The market reference will be at the industrial scale. This comparison is not fair because the lab scale is not nearly as efficient, not nearly as optimized as the industrial scale would be. That's why we use prospective lifecycle assessment. We try to forecast what the industrial scale of your production will look like in the future. So we take data at the experimental level, for example, or at the prototype level, TRL 3, 5, 2 to 6, let's say. And we think of size scaling, obviously. The stoichiometry of a chemical reaction will stay the same, but you need to scale with larger amounts. We think also of process changes. I keep taking the example of chemical production, but you will have glassware at the lab scale. At the industrial scale, you will have maybe batch reactors, insulated batch reactors that are much more efficient. And also process synergies. Process synergies is the idea that the solvent that you use in the lab scale, you might just discard as waste. And at the industrial scale, you might want to recycle that solvent. Or maybe heat reuse could be another example of synergies. And these are all pre-industrial development. There is also post-industrial development. Because we're doing now forecasting, we need to look into the future. In the future, the external system will be different. For example, the electricity grid will be different in 2030, 2035, when your product does reach the market. So you want to account for these changes, and we have ways to do this. And you want to account maybe for industrial learning, just learning by doing. So with the same process, but as you do more of it, you get better at it. Now, I had an example for this. Okay, I'm going to do it quickly. This is an example where we've applied this prospective assessment for a prediction from TRL 5 and TRL 6 to a TRL 9. So technology readiness of the pilot scale to technology readiness level of the industrial scale. And you can see that the inventory values, similar to what we've modeled in the example, change. If we look at energy use, the energy use per functional unit, so per reference flow, decreases because the energy efficiency increases, as you would expect. So this is something that we can model to more fairly represent the potential of your innovation. I wish I could show you more. There are examples of frameworks. You'll have access to the slides and you can look at the links that I have here. And I think it concludes my section, so to say. So with the golden scope and with the lifecycle inventory and with a little bit more added complexity and spiciness with databases, multifunctionality, and prospective assessments. And now I'll give the word to Loelia for the next step of eLCA.
Yeah, thank you. Do you continue sharing? Or okay, do you want me to share?
I can if you like to, but I think it's easier if you do it yourself.
No, it's okay. I just need a second. Okay, so I think you can all see my screen now. So if we go back to the initial eLCA steps that Thomas presented in the beginning of the training, we have kind of finished with the lifecycle inventory, and we are now going to dive a little bit into the lifecycle impact assessment in itself. And so this is where the inventory data that we have prepared before will be translated into environmental impacts. And so I will go into it right now. Okay. Yeah. So we have different impact categories that we are assessing during an LCA, which are, for example, climate change, which is the most famous one, I think, water use, land use, and also some toxicity impact categories like human toxicity, and also some toxicity for the ecosystems, for water, for example, or also for the earth, and also some resource use indicators on minerals, metals, and fossils. And all of these gives us some information about the impacts, the environmental impacts. So if we go into a little bit more details, what we obtain from the life cycle inventory that we performed just earlier is some elementary flows that are then translated into some midpoint impact categories, the ones that I just showed you. So let's say global warming, ozone formation, water use, etc. And those are some our midpoint impact categories, and they can be translated, aggregated into endpoint categories, which are, if we aggregate the blue ones, human health damage, the green one, ecosystem damage, and the yellow one, resource scarcity. We are usually working more on the midpoint impact categories in LCA because we have more information, where using the endpoint impact categories, we have a lower quality of information in the end. So we usually perform LCA using midpoint impact categories. And how do we obtain those results? We use some characterization factors that are used to quantify the impact of the inventory that we have prepared before. So it's kind of a calculation that translates the inventory into impacts. So here you have an example for the ecosystem, where the characterization factor is the result of a fate factor, an exposure factor, and an effect factor. And all of these are available in the databases that Thomas presented before. So here it just expresses how a single unit of mass of a chemical, for example, production contributes to an impact category. And that is what we use for models, for modeling. So I think that's it. And if it's not clear, you can ask me question afterwards. And so it was a very quick explanation, but then if we go into the interpretation of this impact assessment, we are going to obtain results and to obtain some information about the hotspots of our product that we are assessing. And we want to identify also some potential issue on our modeling. And we want to evaluate the completeness, the consistency of the study and of the data we have been using for our inventory, and check the robustness of the conclusions. And that is what I am going to try to explain you in the next few minutes. So here I have an example. So I'm sorry, I didn't find any interesting example about paint. So this is one about coffee, where we, the people that carried out this study compared some conventional drip coffee and some single serve coffee pod. So using a machine with single pods. And we want to know, having those results, which coffee technology is more sustainable. And this is not really easy when you just see those diagrams. And this is where I wanted you to answer some questions so that we have a reflection all together about what type of coffee is the more impactful for the environment. So maybe Beatrice, you can take the hand here for the mentee.
I see 19 people and we are 21. I'm not there, so I think we can start.
I'm not either.
Okay, then it's perfect. So the first question is, what is the main contributor for conventional drip coffee? And you can choose between different options, ecotoxicity, electronics. It depends on the indicator, and I don't know. The mentee is anonymous, so you can just click. There is no correct or wrong. Yes, 4 people left. Shall we continue? Loelia, you want to comment on?
I think I can try to give a first answer. So here what is interesting to answer the question and in the end to know which coffee technology is more sustainable is to first understand what is a contributor. So a contributor here is an item or a process that we are assessing in the LCA and where we are so comparing the environmental impact between one to another. So here the contributors would be the metal, the plastic, the flexible electronics, etc. for the conventional drip coffee. So I think everyone had understood this, and this is why I had some tricky answer, the ecotoxicity, which is not a contributor, but is an indicator. And I think the question is a bit tricky because we can see that the electronics results are, so the yellow bars, and are the almost the highest for each one of the indicator, but not for the respiratory effects. And this is why it would depend on the indicator here. The electronics are the main contributor for most of the indicators, but not all of them. So we can say because the diagram is very small that everyone is right. And we can go to the next question.
Here it is about what is the unit for global warming climate change. Half of the people have already voted.
Okay, so here for the unit, we are referring to the characterization factors that I presented a little bit earlier, which are the way to quantify the impacts. And for global warming or climate change, it is indeed the kilogram CO2 equivalent. And here on the diagrams, you can see that the unit is not written, but the absolute result is written right above the bars for global warming. And this is why I wanted to ask this question, so that it is clear for everyone that the results that are written in the absolute results that are written above the percentage bars have units. And for climate change or global warming, it is kilogram CO2 equivalent. And I think we can go to the next one.
Which coffee has the most environmental impacts?
And so in the end, would you be able to answer which coffee has the most impact? Given the first answers that we had before. So seeing that the results are mostly shown in percentage, it's not easy. I'm waiting a little bit. But we can indeed conclude, because even if it's very small here, and I apologize for that, the answer is given by the absolute results that we have right above the bars. And in a real LCA study, you would have a table with the absolute results, so it will be easier to see. But what gives you the answer here is not the percentage bars. The percentage bars are here to give you what are the most impactful contributors, but the numbers that are written above the bars that have units depending on the indicator you are looking at. And yeah, so that they are the absolute results.
Yes, we can ask a question, Lolia.
Mm?
Can I ask a question?
Yeah, of course.
Yeah. But if I compare the absolute results one by one,
Yeah.
then I see that the single serve is mostly doing better, except in ecotoxicity. So how can I handle this trade-off?
Yeah, you're right. Then in that case, what would be the answer is that the single serve coffee pod is more impactful except for the ecotoxicity, but it will also depend on which indicators you have chosen for your study, of course, because here we only have a bunch of them, whereas as I showed you earlier, we have at least 16 of them that exist. But if we want to have a general conclusion, then it will be that generally speaking, the single serve coffee pod is more impactful for those indicators.
Thank you.
And maybe we can go to the last one because
Can I
time
just
is running.
Yeah.
Yeah.
For understanding. So more impactful means better for the environment, like worse for it, or sorry, the question was not
No,
super clear.
worst for it.
Worst. Okay, and then the numbers up there should be lower or higher?
They should be higher means that the impacts are more important.
Okay, so there's more impact, and
More
that's bad
impactful
in that
and
claim.
more bad for the
Okay.
environment.
Okay, thank you.
Small number, small impact is good. Yeah.
Yeah, that's it. And I think we can go to the last question. So it's very quick. So why is it important to challenge data quality? And this will lead to the next slides that I have to present you. Okay, I think I will just try to answer because time is running out, but here you can answer you can have two answers at a time, and it will be because the results and their interpretation are directly impacted by data quality, and also because transparency and uncertainty go hand in hand. And you should conduct an LCA even if you don't have the highest data quality. You should try to have the higher data quality as you can, of course. But what is important here is to be aware of this data quality and to be aware that the assumptions may lead to some results that are that have some uncertainty, and that is the key of performing LCA and of performing, I think, any of the other dimension evaluations for SSbD. So yes, I think that concludes the Menti sessions, and sorry for being very fast. I hope it was clear. And we can go back to data results about this and data quality. Okay, so just for very quick conclusions, the hotspots here were electronics and electricity consumption. Okay, so if we go to sensitivity analysis and how we address uncertainty in LCA, what we want to have some sensitivity analysis on is uncertain low quality data and also design choices. And what we are doing on the, let's say, the inventory that you performed earlier would be to have some indicators on the reliability, the completeness, the temporal, geographical, and technological correlation. So we give a score to each one of the inventories that you have listed earlier. And so in the end, we have a general score about the data quality that we have in our study. And that's the idea behind that. And depending on the data quality and also on the contribution to results, then we also have some guidelines to follow, whether we should refine, consolidate the data if it's a priority, or if it is a good quality, and then there is no need to revisit the data inventory. So let's say, for example, with the coffee example from earlier, for the electronics, if you have, so you saw that we have a very high contribution to the results, but depending on how the study was carried out, if the data quality was low, so let's say we don't have any info and we just use some proxies that we don't really know about, then this will be priority to be consolidated as data quality. So that's what we want to address when we are listing the inventory. And just to show some examples of what can be the impacts on the results depending on the assumptions you make, on the data quality you choose. This would be an example of a single bottle compared to some reusable systems, so different scenarios. And depending on the choices you make for the different scenarios, then the break-even point between the single use and the different reusable scenarios, it changes drastically when the hypotheses change. So it's very important to know where you are at on the sensitivity and the quality of your data and of your assumptions when performing an LCA, because the results can vary depending on the choices you make. And you can see here some other examples. One where you have some scenarios depending on the locations of different processes. And you can see, of course, that I didn't choose the right example because it's a social index. Actually, it's not environmental impact, but it's the same thing. You will have some different results depending on the scenarios, assumptions that you have made. And it is the same here with some scientific assumptions also. So some time of operation, some distance, and yeah, you have different possibilities of scenarios when assessing. So for example, with the paint example that we had earlier, this sensitivity could be carried out, for example, on the power of the milling machine. So it would depend on what would depending on what the power would be, then the results can be very different. And so there are two types of sensitivity analysis. One which is local, where we have a one at a time approach. So it is where we will change each scenario or each item of the inventory one by one. So it's the easiest way, but it's also time consuming and not as efficient. And we would have also a global one, where we have some screening data collection, and we try to address what are the different parameters that can change, that can vary, and then with some mathematical analysis, we can obtain a global sensitivity analysis where the different parameters can change together. So I have a more detailed slide right here. And so with some different iterations, you would propagate the different uncertainties, the different factors, the different parameters to obtain results of the sensitiveness of your different parameters. And that would be one type of conclusion. And I'll go very quick here because I'm out of time. And just as a last slide on this topic, there are different sources of uncertainty. The first one is parameter, so linked to the data quality that I presented earlier. The scenario also, so it's more linked to the choices of modeling you make. And also the model in itself, so linked to the methods. As Thomas presented, the databases that exist, there are also some methods that exist and that we can choose. So for example, the environmental footprint method, and depending on the one you choose, some uncertainty can come out of that. So I'm done with it, and I hope I was clear. And I think, yeah, Martin is going back to you.
Yeah, thanks a lot, Thomas. Thanks a lot, Loelia, for really doing this nice show of the slides and overviewing all that. What have we seen? Also thanks to the other moderators, Laura, to Carla, to Stephanie, and to Vanema for the breakout sessions. What did we see today? So we went through the phases of the LCA in detail now, in much more detail, I would say. We did quite a good exercise on goal and scoping, and then did this joint interactive session on this inventory building in the mural, which will be available as PDF afterwards as well, and can be practiced on later on. We heard a bit about the relevant databases and some peculiarities. I guess we will come back to databases in our series again and again, of course, and also the topic of what was discussed lately on the sensitivity analysis and how to deal with uncertainty will probably also be covered in the other LCA sessions that we're still having in front of us. It was also nice to hear about prospective LCA, and quite relevant for earlier stages where the differences are, how to do it, was a bit too much for today, but I guess we have dived a little bit into that. Thanks for that. We learned about endpoints and how the midpoints that are generated from the elementary flows are accumulating for the different aspects. Yeah, and then we heard about characterization factors, the influence, of course, the impact assessment. Maybe we are also going to be reiterating on that one. More discussion may be needed. What are the different characterization factors? I guess on specific examples, we are going to be seeing that much more. So I guess it was a very good training. What are we going to be seeing next? So that today we had this environmental LCA, and then we are going to be continuing in December with LCC, so life cycle cost analysis. and then have in the new year a training on social LCA. And then later next year, we are also going to have a training on decision support, multi-criteria decision analysis with our colleagues. Thanks a lot to all of you. A last round for comments, questions. So doesn't look like at the moment, at the spot, it was an intense session. Thanks a lot. We will upload all that. Thanks a lot once again to the people who prepared that. This was really lots of work, and it was very creative and very nicely done. Thanks, Thomas. Thanks, Loelia. Thanks, Laura. Thanks, Carla. Thanks, Stephanie and Ponema. Thanks, Beatrice, a lot for helping with all the technicalities. Yeah. See you.
Thank you, Martin, for coordinating, and thank you all for participating.